What's up, YouTube? It's Mr. Tooler back at it again with another video. I'm really excited for this one, guys. Back on the channel with 5.2 inverse relations and their graphs. Before we get started, as always, if you enjoy the content, don't forget to subscribe. It really means a lot. It makes it so that I can keep doing videos like these for you guys. So thank you. And at the end of this video, if you like it, hit that like button. Okay, 5.2 inverse relations and their graphs. It should say and tables. Okay, we're going to be talking a lot about graphs and tables today. Okay, what I want you to do is flip. We're on page 85, by the way. I want you to flip the page to number 2. Imagine your dream car. Maybe it's a Ferrari 550 Monterello, a super fast Italian car. Experiments have shown that on smooth, dry roads, the relationship between the braking distance, d, and the speed, s, is given by distance of speed equals 0.03 speed squared. Speed is given in miles per hour, and the distance is in feet. So what are we going to do to start this problem? How many feet should you leave between you and the car in front of you if you are driving the Ferrari 55 miles per hour? First of all, what we're going to do here is obviously big Bing. We're going to do a really big Bing on this question, okay? On top, we've obviously got our, let's see here, our Italian sports car. And on the bottom, we've got, I'm making stuff up, guys. All of that to say we're skipping page 86. Flip the page to the next one. What if the driver of the 550 was cruising, suddenly hit the brakes to stop because she saw a cat? She skidded to stop and fortunately missed the cat. This was just a small typo. It should say unfortunately missed the cat. I'm kidding, guys. I'm kidding. We're big binging this page as well. Big Bing, page 87. Okay, that brings us to page 88. Page 88, guys. This is what we're going to do. We're going to big Bing 9 and 10. Look at this. This is all we need for today's lesson. Now we're into the real stuff, guys. Lock in for me right here. Functions. Functions are like a machine. Let me get you a machine going here. Let's say we got a machine. Well, no, I don't like that machine. Trying my best here. Okay, I like it. A machine. F of x. Functions are like a machine. If we plug in a number into our machine, f of x, you guys are just kind of watching this, by the way. If you want to draw this at the end, I'm going to probably be erasing and drawing us all sorts of things into this machine, but I just want you to pay attention to what I'm talking about in terms of this machine. Like we learned last time, guys, functions are like a machine. We plug a number in, and we evaluate, and we get a different number out. Okay? In other words, we give our function an x value. It goes into the function. We evaluate, and it gives us a y value. Y is also known as f of x. It is x evaluated into the function. Okay, functions are like a machine. Today we're talking inverse functions. Okay, so I could have kept that. This is like an inverse function. Our normal function machine, we're going to plug in an x. We get out f of x. What about a machine for the inverse? I think this will help you guys visualize this as well. Okay, inverse functions are written -1 of x. Okay, and in this case, if these two functions are inverses of each other, that means that they are exact opposite functions. They are exact opposite machines. Meaning, if I take whatever I got out right here, and I bring it over here and plug it in, I'll keep it color coordinated. Guess what I'm going to get out of this machine? I'm going to get out an x. The same exact x that we started with. It's like a cycle. So a lot of times I use the words input and output. We give the original function an input. It spits out an output. If we know the inverse function, we can take the output that we got above, and it will spit out, the inverse function will spit out the original input, the OG input. Okay. So the inverse function gives the input of the original function's input as its output. Input, output, output, input. Plug in an input into a function, get an output. Take the output, put in the inverse, get out an output that was the original input. Okay, I'm going to let that sink in for a second. Seventh period. Ben, I know you're getting it, man, but you just got to be patient with those around you. They just take a little bit longer than you. It's all right. Eighth period. Paul, that deep question you're thinking in your head right now, ask it when I get back. I'll be glad to answer it. Okay. Inputs and outputs. Let's say we have a table here. Here's our functions, our function, singular. These are my inputs. What we're saying here is we don't know what the equation is. There's an equation. It could be 4x plus 2x minus 4x squared minus 2x minus 3. It could be a full-on equation. We have no idea what it is. We're taking the number 2, and it spits out a 0.5. That's what this table is telling us. If we input a 2 into the function f of x, it will spit out a 0.5. If we plug in a -1, it spits out a 1.5. If we plug in a 0, it gives me a 4.5 and so on. So now what it wants us to do is write a table for the inverse function. Okay? So what number would we plug into x into this inverse? Well, all this is going to be, guys, is the outputs of the original become the inputs of the inverse. So, for example, if I plugged in a 0.5 into the inverse, guess what number I have to get out? A -2. It completes the cycle. If I plug in a -1 into the original and get out a 1.5, that means if I plug in a 1.5 into the inverse, I get out a -1 as my output in the inverse. 4.5 would give me a 0, 13.5 would give me a 1, and 40.5 would give me a 2. Okay. Let's try the next one. If I input a 2 and get out a 3, that means in the inverse, I have to plug in a 3 and get out a 2. This might be the easiest thing we've done all year. Okay. You literally flip the columns. I don't know what else to say to you guys. Okay, now, you may be asking, why do we skip all this? Well, it was kind of an intro into simply plugging in inputs, or getting outputs, and how that relates to putting the output into the inverse. Why our inverse is important. We'll get into that next lesson a little bit, but we would do a couple graphs here up in this stuff, and I think we're able to cover it with these graphs here. These are graphs. They have multiple points on it. It's asking us to graph the inverse of the function that's currently graphed. So we'll do it in red. These are each ordered pairs, x, y coordinates. This is 0, -2. This is 2, 1. This one is 3, 5. And this one is 4, 13. Okay, let's look at the point 0, -2. If this is the input and this is the output, x, y, the inverse's point is just going to be flipped. That's it. We're flipping the x and y values. So this point becomes, I said I was going to do it in red, I'll do it in green. Getting in the Christmas spirit. -2, 0. 2, 1 becomes 1, 2. 3, 5 becomes 5, 3. And 4, 13 would become 13, 4. That one's not really on the graph. So we can just draw this. And that green graph right there, guys, is the inverse graph of the blue one. The inverse. Okay. We'll do this one over here just to have more space over here. There's only 3 points. Point right there. This one is at 3, 1. This one is at 2, 2. This one is at 1, 5. So all we're going to do is flip these points. 1, 3. Do it in red. 2, 2. If you flip it, it's going to be the same point. And then 5, 1. This is what the graph looks like. That's what the graph looks like, guys. If you made it this far in the video, thank you. Don't forget to hit that like button. Subscribe, share with a friend, hit that bell so you don't miss another video, guys. I'll send you off with a sticker, a motivational sticker for you. Remember, 24/7, 365. Math it up. That's the motto I just came up with. Math it up, guys. Enjoy your homework assignment, and I'll see you soon.